Welcome to another Leetcode problem. Problem number 126, word ladder 2. This is the hardened version of the previously discussed word ladder 1. This time they are not only asking you to send the shortest path, but they are asking you to give all the possible shortest path to reach the end word. See here, the output expected is not only a single number that is telling how many nodes should be there in the shortest path, but the both shortest path from the starting word to the end word. The first list here and the second list here. So here all the shortest path we have to return. Previously in word ladder 1 we simply did the BFS, and moment we identified the shortest path we are returning the length of the nodes in the shortest path. But now we cannot simply return from there. We have to record that path, and we have to record all the shortest possible paths to that particular end word and return everything back. Here BFS alone is not going to be sufficient because we have to return all the nodes in the path. It means we need a way to traverse back to the begin word from the end word. So in this problem, while we are doing the BFS, along with normal BFS, we are going to store the parents of every node, and we are going to use that to traverse back to find all the alternative paths. Suppose if you haven't watched the previous video, please watch that to understand the problem, to understand the BFS and the graph creation concept in that, because we are going to reuse that here. Please pause the video. Please go to the previous video, for which I have given link in the description. Complete it and come back here. At that time this video is going to make more sense for you. Now let's discuss the solution. This is the graph we have constructed in the previous problem. Let's make smaller change here to understand it better. Let's just remove dog and log. Instead of that, let's have bot and bog. In that case, the graph is going to change. We removed dog here and log here. So this length we can remove. Instead of that, we are having a bot, and bot is a neighbor to dot also and lot also, because there is only one letter difference. Instead of D there is a B, and instead of L there is a B, so both are neighbors. And then we have a bog, bog is a neighbor only to bot, because there is T and G and there is no B in any other words. So this is a neighbor to bot only, and COG is a neighbor of bog, so COG has no other neighbor. This is a newly augmented graph. Now let's try to find the shortest path from hit to cog. So if you are starting from here, you can go 1, 2, 3, 4, 5. This is one shortest path, and second is like this down to 3, 4, 5. This is also 5. There are two paths like going from 1, 2, 3, 4, 5. Total 6 nodes are here. This is one path, and second path is 1, this is 2, this is 3, this is 4, and this is 5, this is 6. So we have to return a two list. One list is going to have these nodes, other list has to have these nodes. This should be the final output for this particular problem. So what we are going to do here is, while doing the normal BFS, we are going to record the parent of every node in this particular graph. I hope you understood BFS very well from the previous video. If you haven't watched, please, I recommend once again watch that video and come back here and continue. So here in the normal BFS walkthrough, we will start from the HIT. When we start from this particular node, whenever we are visiting this node, we are going to update its parent. So hit is not going to have any parent, so it is going to be empty for HIT. For HOT, the parent is HIT. Also, we can say LOT and DOT both are parents, right? Because when the edges are undirected, we can say if HOT is a parent for DOT, and we can say DOT is also a parent for HOT. But we don't want to store them as a parent here, because from the begin word to reach HOT you just need only one edge. But if you are going to reach HOT from DOT, if you start from here, go here, come down, go and reach. So there are 1, 2, 3, 4 edges. So obviously any path via DOT and LOT is going to be longer than the path via HIT. We don't want to store DOT and LOT as a parent for HOT. How are we going to do that? In the BFS, you remember we were maintaining a level. So if the parent level, so currently we stored HIT as the parent for HOT, right? So if this level, HIT's level is going to be initially 1, or any other parent which you are going to store for HOT, if their level is greater than the previously stored parents, we are not going to consider those parents. So in this case, HIT will have parent level 1 and DOT will have 3, LOT will have 3, and these two values are greater than 1. So we are not going to account these as the parent here. So we are going to only keep HIT as a parent for HOT. When we go to DOT, we will have HOT as a parent. There's a possibility we can say LOT also as a parent, but as I told you previously, the level for HOT will be 1, HOT will be 2, this will be 3. We already have a parent with level 2, we will not add a parent with level 3. So for DOT, we are stopping at HIT itself. Similarly for LOT, it is going to be only HOT. We are not going to add DOT as a parent because of the level difference. So this stops with HOT. But when it comes to BOT, we will have both DOT and LOT as a parent. So this should have both parents because the level will be 1, 2, DOT and LOT will have both are 3 and both levels are same. So we need to have both of them as a parent for DOT. And for BOG it is simple, it is only going to be BOT. And for COG also we can simply store BOG, but actually we are not going to store the parent for the final word because we have already reached it. So we just need to calculate all the alternative path BOG and append COG with that. So let's try to add alternative path for BOG. So let's see what are the alternative path to reach BOG. First it is going to be HIT to HOT, then DOT, then BOT, then BOG. So let's write it down. It is going to be HIT, sorry, I will use this pen. HIT, HOT, DOT, BOT, BOG. This is one path, and second path is going to be HIT to HOT, HOT to LOT, LOT to BOT, and then BOG. Let's write it down. HIT, HOT, LOT, BOT, and BOG. Now let's simply append COG with these two paths. We will get the final answer. So let's put COG and COG, close the list and send it as a list of all the list back to the caller. And this is the solution for this particular problem. Let's go for implementation. Let's start the implementation with the boundary check. If the n word is not part of word list, let's simply return empty list. And now let's initialize the variables. Shortest path which we are going to return, which is going to be a list of list, we will initialize that to empty list, and BFS queue and visited and level. Initially we are going to set this to 1, but inside the while loop we are going to increment this. And before going into the while loop, we need to set the parents and parent levels variables. Let's add the begin word also. Similarly, let's add the parent levels and initialize all the parent levels to infinity. Let's set one for the begin word also. For begin word, we can set the parent level as 0, and it is not going to have any parent, so we don't even need to set this, but it is okay to set it to 0. Now let's start the BFS by enqueuing the begin word into the BFS queue. Start the while loop, while BFS queue. Let's increment the level. As we know, we just need to traverse only the particular level. It means we need to traverse only the number of elements currently in the BFS queue. We should not traverse any element which are going to be entered into the BFS queue. So for that we'll have for loop. Inside the BFS queue, let's dequeue the node. Now we have the node. Let's traverse all the neighbors of this particular node. Get all neighbors for node. So let's not worry about this function. We will implement it. Anyway, we don't need to maintain an adjacency list because we can dynamically determine what are the neighbors for a given node. So we are going to implement this in a moment. For now, let's assume this function can able to return all the neighbors for any given node. And first let's see whether the neighbor is a end word. It means we have reached the end word, and then we have to collect all the path to the end word via the node. So let's try to get all the alternative paths to reach the node, and then let's append the end word with that and store that into the shortest path. So let's assume this function is going to give all the possible path to reach nei, and that is going to include neighbor also. So now we have to add end word into the path and store that into the shortest path. Plus end word. So now this will have all the paths to end word via node. But we cannot simply return here because we need to finish the complete traversal of this particular level. It means there may be other nodes that may lead to the end word. So currently we just stored all the shortest path to the end word via this particular node. There may be another node into the BFS queue that may also lead to the end word, right? So let's not return that. We are just storing that value into the shortest path, and let's do the check once we finish the level. Let's have a if check here. Once the for loop is over, if the shortest path is not empty, then we can return the shortest paths. If it is greater than 0, we return shortest paths. We don't need to traverse any more further because all the further paths are going to be lengthier than currently stored path. But this check we have to do only after finishing this particular for loop, because this particular for loop is handling the levels. Now we handle this case. Suppose neighbor is not the end word. What we have to do is, first we have to see whether the neighbor is in the visited. If it is already visited, we can simply ignore. We are continuing. For this we have to add this node into the neighbor. We missed it previously. Okay, now the node is not in visited. In this case we have to add the node as a parent to the neighbor. Right, because we reached the neighbor from node only. So node is a parent, one of the parent for neighbor. We have to append node into the parents of neighbor, and before that we have to check whether the neighbor already has any other parents, and if those parents are having lesser levels, we don't need to add this particular node. So let's check if parent levels of level is greater than or equal to current level, we can simply continue. We don't need to add this particular node into the parents of the neighbor. Otherwise, let's update the level also. So this is not an append, it is a set, so we have to add here. If the neighbor is not in BFS queue, let's append that into the BFS queue also. Okay, but if we have finished the entire traversal, the while loop is over, we have to simply return the empty. Shortest path is going to be empty array and we are returning empty, saying there are no shortest path from the begin word to the end word. This is the core implementation logic. Initial boundary condition we are checking, then we are initializing the variables, then we are doing the BFS. Inside the BFS, we traverse level by level. Inside a level, we take one node from the BFS queue, then we add that into the visited check. Then we are taking all the neighbors of that particular node and see whether we have reached the end word. If we have reached the end word, we gather all the possible path to the end word via the node and store that into shortest path. And we are not returning that immediately. Suppose the neighbor is not the end word, we are checking whether we have already visited the neighbor. If we have visited, continuing, we are not doing any processing. Suppose the neighbor is not visited, we are going to update its parents. Before updating the parents, we are checking the level of its parents. If the level of the neighbor's parents are greater than or equal to current level, not greater than or equal, it should be less than or equal. If it is less than or equal to current level, we can simply continue because we don't need to add this particular node into the parent list. Why we are doing this check is, suppose if the neighbor has any other parents that is having lesser level than the current level, to reach the neighbor we can come via that parent. That will be much more faster than coming via the current node. That is why before adding node into its parent list, we have to check whether this is adding any more alternative path which is going to have shortest path or not. So here it should be only less than, not less than or equal to, and when the current level and neighbors previous parents are having same level or the previous parents are going to have higher level, we are updating the neighbor's level as well as we are adding the node into the neighbor. Then we are checking whether the neighbor is already there in the BFS queue, otherwise we are appending that into the BFS queue. At last, after processing this particular level, we are checking whether we have found any shortest path in this level. If we have found shortest path in this level, we are simply returning that. We are not doing any more processing. Now we need to implement all the helper functions. We have two helper functions required: get all neighbors and get all possible path. Okay, let's have them as a class function, so we can keep it as self dot. This is also going to be self dot. It is a definition, and to get all the neighbors, not only node, we need to have the word list also. Word list is currently a local variable. Let's pass word list also here. So we'll get it here. Let's have a global variable to cache the relation. Let's initialize that in the find ladder function itself. We'll have adjacency list. AL is going to be and AL of is also going to be a set. We are not going to fully initialize the adjacency list, but whenever we find a neighbor, we are updating it. So we don't need to do the processing again. Let's use, this is going to be self dot. So it is a class variable, and that we are going to use it here. So for word in word list, if both are neighbors, how to see if is connected node comma word, we need to have a neighbor list. We have to return all the neighbors. So let's have a list here. So it is going to be neighbors plural. So both are connected. Is dot append word. What we can do is we can check the cache here. So before even checking, calling the function, we will have the check if word in L of node already, then we can add. We are checking the cache, and in this case we have to update the cache. L of node dot is going to be a set, so add word, and similarly al of word we have to add node. And let's implement the is connected function. W1 and W2. This is going to be same function which you have implemented in the previous program. So we will have a diff which is set to 0 for I in range len of W1. W1 of I not, it is going to be if W1 of I not equal to W2 of I. So this is a W1 of I. Then if diff greater than 0, return false, otherwise diff plus 1. From here we can return true safely. So this is connected function which we implemented previous program also, it is same. So we implemented get all neighbors, it is returning all the neighbors, we have to return it at the end, which we forgot to do. Now we have to implement get all possible path for neighbor. So these definitions are a little weird in Python. So it should be self as an argument here, not as a definition. This is also going as an argument. Self comma will get a particular node. Also we need to have a parents, and we have to pass the parents from here because parents is not a class variable, so neighbor along with parents. So let's process it here. So inside this function, first let's just return the node itself if it doesn't have any parent. So the begin word is not going to have any parents. So let's simply check if there are no parents. If not parents of node, return just the node as one particular list. It is going to return list of lists always. So we are simply returning the list of nodes. Otherwise, let's define an alt path variable. This is going to be list of the other list which we are going to generate. And let's traverse every parent of this particular node. For parent in parents of node, and let's get an alternative path to reach the parent. For path to parent in self dot get all paths to reach parent, not the current node. So it is going to be parent comma parents, and we will append alt pass dot currently got the path for the parent plus the current node. So this is an extension of the previous, the path for the parent along with the current node. So if there are multiple parents and every parent is going to have multiple path, we are going to append the node with that particular path. So we are going to have a cumulative list of all the alternative path of all the previous parents. And once we have this for loop, we have two for loops are over, we can simply return the alt path. Okay, the implementation is complete. We can run this code with test cases. We got some error. It says cannot access local variable node which is not associated with the value. Okay, for node in word list, not word in word list. List object has no attribute pop left, so bfsq is a list. We will make it as dq. Let's rerun. Okay, name al is not defined. Did you mean self.al? Yes, it should be self.al. Adjacency list is actually a class variable. So word in self.al, we are returning this. Also should be self. We are updating the class variable. Let's run this one. Solution object has no attribute. Get all possible path. So what is the function name? Get all possible paths, not path. It's a plural. Okay, where we are calling possible path. Get all possible path. This is get all possible paths only. Another place is get all possible path. It should be plural. Let's run this again. Nay is not defined. Alt path in the path NEIGH. Cherry spelling mistake. Rerun this. Too many mistakes we have done today. List object has no attribute append. Okay, spelling mistake. Run it again. Test cases are failing. So word list output is coming like this. We are appending cog twice for some reason. Let's see what we are doing. Alt path to node, not neighbor, because we didn't update the parent of neighbor, and we are adding the neighbor at the end of the alt path to node. Let's run this one. Okay, all test cases successful. Let's submit this and see. If you like this video, please don't forget to give a thumbs up and please subscribe to the channel for more such videos. Thank you for watching.